We're live. Hello, I am Junchan, and we're back at working on Chronofolds and specifically developing a Purescript version of the data structure. And let's see, let's start with a little bit of housekeeping. And we are the 30th, I believe, and so let me create a new log for today. I actually done some change to the log yesterday off screen, so let me maybe walk you through these. But maybe before, let me make sure I got my checklist done. Mic seems good. Yeah, I need to start the music. And here we go. Okay, so did a little bit of changes to the log. Changed a bit the disclaimer. I do like to follow tangents, but I do pop back the stack. I come back to wherever I was, where I was eventually. Though everything might change without notice, and you know, I'm streaming as an experiment in working and learning in the open. So I've never done a Purescript library before. I've never done an implementation of a data structure from a paper before. Never really done much work with CRDTs. So this is all new, and this is me discovering this, and hopefully that's of some interest to others. And I've also annotated that what we have on our workbench right now is this work on Purescript Chronofold, and this will usually take place during the weekdays, and some of our upcoming tasks there. The next one is to implement the causal tree merge algorithm. That's what we're working on last stream, and we'll continue to do so, and as we do set up some tests. And I also realized that one of an interesting sort of midpoint, I'd say, with the library before getting into maybe performance and other APIs is to build some kind of prototype on top of it. And I thought maybe something that would be quite good to try and do would be to publish this very log as a real-time syncable data structure, maybe through a Twitch extension. So that's an idea. And then we can look at things like performance and APIs, setting up benchmarks and so on. And then I'm also going to be streaming over the weekend, and Saturday at 4 p.m. I'll be streaming around streaming tools. And one of the things that I was wondering on my last stream about streaming tools was how can we basically bridge the gap between Twitch and YouTube, or streaming and sort of archived video that maybe are a bit more edited and fit for use on platform like YouTube rather than three hours. And you know, 3 hours of streaming. And then some idea was given to me by Chris Spanner a while back on stream to do a blog post about something, and I haven't really scheduled any session for that. And I should note also that when the new year starts, I will be taking on a new full-time job, and so that means that I probably adjust these times here, but more about that some other time. And yeah, please talk to me about these things if you're interested in them. I'm also interested in them, and those are tangents, in my view, definitely worth following. And that's some stuff that we did last time, and we can sort of reset that. And something that maybe we can work on our next streaming tools stream as well. And I've added the link to the Git repo where we are working, and I pushed our last work with our failing test for the merge conflict, which is really where we left things off. So that's it for the preliminary announcements, and we can go and dive back into our test by maybe doing simply a run test. And if we take a look at our tests, we were working with, I realized last time that in fact, the example that's given, and that's not this one, it's actually not a merge conflict example. And so I dug up this blog post here, which we looked at also a while back, and that is definitely a merge conflict. And so now we have a proper test implementing this example where we have a replica 1 that has ops cmd, a log containing characters C, M, and D, and then we replicate that to 2 and 3, side 2 and 3, and then 2 adds del at the end, 3 adds alt at the end, as we have here and here, and then 1 enters 2 backspaces and then TRL, which leads to then its content being CTRL. And then we replicate and we try and check whether the log in 1, 2, and 3 projects properly to control at the alt del, which it doesn't because the conflict merge is not implemented. So that's what we're going to be working on right now. And I wanted to run test node, which is going to be the fastest way to test things here. There we go. All right. So what is supposed to be the algorithm? Well, let's see. I don't know if it's actually best described here or best described in the in maybe some of the linked paper, but let's take a shot. It inserts the up after its parent, so unless it finds preemptive CT siblings at that location, so that's what we are wanting to detect here. And I suppose we can do that by going to data structure and check where we were. Yeah, I was thinking that we could detect whether there was a CT sibling or not when we were implementing the next when we were finding what is the new next array, or co-structure as it's called in the paper. And I guess that's a potential one. Another one would be in the causal tree detection. And yet another one would be to actually do this during the rendering, or what I've called the projection here. So let's read this part of the paper and try and make some decisions here. So let's see. Insert the up after its parent unless it finds preemptive CT siblings at that location. Those are ops with greater timestamps, also having kgamma as their parent. If found, the new op is inserted after preemptive siblings and their CT subtrees. If explained in HAR terms, the CT parent becomes left co-object with preemptive siblings becoming succeeding nodes with greater timestamp vectors. In terms of 2010 paper, those are parents or unaware siblings. In plain words, preemptive siblings correspond to the concurrent insertions into the same point of the text. It is the trickiest part of CT-RGA, as it is an algorithm within an algorithm with somewhat different properties. Still, it is considered a worthy trade-off because it keeps other parts simple. In real-world usage, preemptive siblings are very rare. Note that the Chronofold building algorithm uses information that is not included into the Chronofold itself, namely in the tree-forming ref and so on. If we edit only okay. Okay, let's see this. Namely, as per remark 2.3, the timestamp of a newly locally authored op is greater than all the timestamps in the log. Yeah, that excludes the case of preemptive siblings, so ndx minus alpha is not needed. ndx alpha inverse. So here there's the hint that ndx alpha -1 is really needed when we need to detect the preemptive sibling. Which is interesting because it seems like maybe I've already in fact used it. ndx inf. This is just this is next, so that's not, we're not looking at ndx inf here. Where we're looking whether we are actually appending at the end. So we are looking at it. ndx alpha -1 is not needed. Well, it's not needed, but don't we need it to be able to say whether we have a consecutive operation or not? In my case, is done by looking at oref. And we look at the value of oref inside our ndxm to do this, the relinking, that's for sure. So maybe that's something that I want to take a note of. Because that's something maybe I want to contact the author about and just double check. And maybe also double check with the Rust implementation. Okay, where could I put these? Like maybe in open questions. Check with author and Rust implementation. This timestamp of a newly authored op is greater than other timestamp in the log. Where? I should point to a specific comment. In the course structure. Right here. So my question would be, Don't we need ndxinf to check if the op is sorted is insertion or an append. That would be a way to ask this. Okay, the index of the preceding character should be already known. So ndx alpha is not needed either. That seems like that's something else that we don't quite do. So let's add this. I don't know why it's the space are mangled. ndx alpha I is not needed either. Okay. Then the data from ref ndx alpha minus 1 can be kept in a separate data structure, thus removing it from the code path. And we're definitely not doing that. But here we're saying we merge the op and then we read it many times. Does this mean this is done at projection? Simplest way to store that metadata is to keep a secondary log of op timestamps and their ref indices, and to implement index alpha minus 1, simply read that log at the index j. And to implement ndx alpha, we may need to scan it from position k to the end in the worst case. Oh, okay. So, interesting. So that's quite a different take than what we've done so far, because we do have ndx inv as an array of timestamp, indeed, but we don't scan it. We have a map for the a map for the reverse lookup. So I guess we're adding some space. Maybe that's a trade-off, right? So ndx is not materialized in the paper. Instead, it scans ndx inv. Okay. Oh, and we scan from position k to the end. Interesting. That costs ON, and from that perspective, we might be tempted to store that mapping in a hash map, which I've done. That would solve the problem on paper, but as it was described earlier, that may not be a good idea in practice. Okay. One way to avoid those worst case scans is to keep a separate sorted table of index shifts. Namely, once make a shift table entry shift. Having the entry, we know that blah, then ndx blah. As long as this is correction keeps us within t steps on the target, we do not need additional entries for beta. This technique is improved in section 4. I see. So instead it's scans index or uses a shift table. I see. A separate sorted table of index shifts. A separate table of index shifts. Okay. With the shift table, index has complexity O log n, which means O log n insertions, except for one adversarial scenario, namely the op has ON CT children, which are fed into a replica in the reverse timestamp order. Okay, yeah. Then the case of preemptive siblings turn into the bubble sort algorithm, or in per op or in squared total. The scenario corresponds to lots of concurrent insertions into the same point in the text. Due to the properties of causal consistency, one author cannot send ops out of order, so this scenario should probably include a Sybil attack too. There's another Chronofold building algorithm that lacks this unfortunate corner case. We have to skip it as it depends on many techniques not explained here. Oh, okay, interesting. To illustrate what we achieved here, let us consider two typical versioning operations, recovering a past version and deriving a difference of two versions. And those are interesting, indeed, operations to implement in their own, maybe, version module. But before getting into that, let's see what is the point made about the hash map, which is said to solve the problem on paper, but may not be a good idea in practice. So let's search for hash map. Hash map. I can't see the highlight. Okay, it's still in the same place. Oh, okay, yeah, I'm not. Still mapping in the hash map. Oh, there's only one map. There's only one. Okay, so per symbol hash map. Use the peculiar optimization technique coding timestamps as a tuple of characters and using regex scans to avoid keeping a per symbol hash map. Okay. RGA needs a hash map to store a linked list. One entry per character. A naive CT operation may store a text as an actual true letter. Sub-implementation are known to exist and they don't work well. Overall, turning a character into an object means lots of overheads. CRDT overheads and complexity are rooted in the use of per character IDs and the need to map them to positions in the weave and the text. That data has to be stored in addition to the regular editable text data structures. According to the original article, RGA needs a hash map to store the linked list, one entry per character. So that would be turning a character into an object. I mean, we are kind of doing that, but maybe the fact that we're doing co-structures is somewhat obfuscating the fact that we're doing that, but I guess we are. It'd be interesting to benchmark this without this optimization and then and also test them like property tests them and benchmark them with the property tests and maybe even fuzz tests, and then try to maybe remove this intermediary data structure and see how this goes. Okay. So that's what there is about hash maps in there. Okay. So really the whole preemptive CT algorithm is simply, if found, new op is inserted after preemptive siblings and their CT subtrees, so their whole subtrees. And that should be fairly easy to do. And the question is, do we do this on write or on read? And I'm not sure, even after reading this. Inserts the op after its parent. Let's look at this here. So in this example, I'm confused by the term insert here, because this seems like a splicing. But it probably isn't, but maybe here would explain it to us. I mean, this is, yeah, this. If this is the chronofold and the dashed boxes are the co-structures, then this is inserted here and as deletes and then writes lobace. And so that's a typical example. Then that's indeed appended at the end. So then it would be on read that we do so maybe that's a question for the README, right? Unclear which operations are on write and or on read. Specifically, the well, what do we have? We have a few things. We have the weave relinking, right? The linked list relinking, and then we have the preemptive CT sibling insertion. Those are I think the two expensive operations we're doing here. Although because we have our maps, those two things are maps right now, so that's and maybe I should call this well, no, I was gonna say call this naive, but I think I'll change this when I start going further in the implementation. Okay, so one question then is, how would we, let's try to somewhat arbitrarily decide that we do the preemptive CT sibling insertion on read instead of on write. So what does that mean? Here we are scanning the log, and we're doing so by, in fact, just following the linked list. And so if we do that, then at some point when we follow the linked list, in this case, we'll arrive at maybe our second backspace, in fact, sharing a CT parent. How would we know that? We'd be following the linked list. We'd be going to 1, 2, 3, and then 4 would be the first delete. 5 would be the second delete. Here at this point we look into what I called array index, but is really, or where NDX is, but it's really next. It's not the NDXs, it's the nexts. And that's the index of next, or NXT, to avoid shadowing. And we do pass it next. And maybe we watch this. Okay. So once we found the next character, I guess we also do want to check whether that next character has a preemptive sibling or not. So does the next character have a preemptive CT sibling? And by preemptive we mean someone with a, it means we need to do an ordering or use the ordering between timestamps. And how can we check that? We can, well, first of all, are we going to need the ref? Feels like I'd want to model this example, but using our notation. So let's do this. Actually, didn't I start that? I did, yes. Okay, so let's take it and put it here. But let's also take some of the stuff we've done here, because the notation, I think, is more polished. And so what are we saying? We're saying we're doing this first, such that one log CMD which I suppose we can call alpha in this, which is a bit inconsistent, but I think it should be okay. 3 alpha, 4 alpha, and that would be, next would be 2 alpha, I believe, and so on. And val will be CMD. And the timestamp will be alpha 1, alpha 2, and alpha 3. And ref would be alpha 1, alpha 2. Oh. Yeah, alpha 1, alpha 2, alpha 3. Like this, I believe. And so if we follow what we've done before, then what matters next is what happens with 2. And specifically 2 ops del. It depends on alpha 4. But its index is, or its timestamp is alpha beta 5. And its value is del. And so this is really then beta 5 and beta 6. And this is beta 6 and beta 7. That, I think, makes sense to me. And then we'll have our 3 ops alt, which is going to be gamma 5, 6, 7. Also depends on alpha, and therefore gamma 5 and gamma 6 here, and I made a mistake here, 6, and it will be A, L, T. And finally, we'll have our one up backspace 2 TRL, which will be alpha 5, 6, 7, and we'll have 2 backspaces and CTRL. Oh, sorry, TRL. And so it's actually alpha 8 and alpha 9. And it will be nicely contiguous here. And we can remove this and this whole other nonsense and have 3 ups LT here, and then our 1 up backspace to TRL being this. Okay, so that's fine. And then it's when we append that things get interesting, right? I mean, one thing we could do is indent this. To reflect that there's a kind of an alignment like that. And suppose we can do this like this. And then I suppose we would want to also describe what this guy looks like, which is maybe where things are a bit more interesting. Because that's just going to be contiguous here. Well, contiguous here. It will turn out to be also contiguous here. And to be 2 backspaces and TRL, and this will be inserted. Yeah, because in this view that's contiguous, so it's all right. And same here. So that's sort of very uninteresting, but things are, I think, interesting then. Well, they're interesting when we start doing the first merge, so when we start appending the 2 ops DEL here, right? So let's so that's, yeah, that's in fact not right. I mean, we do, yeah, that's in fact that's 1 log CTRL that we have right here. So maybe we also make this one explicit. And but when we add 2 ups del, then here we have new things coming up. these timestamps. With these refs. And DEL. DEL is not here. DEL is here. And these are in alpha. And therefore we need to relink our linked lists here because we were pending at beta 5. Sorry, at alpha 4. And that's really, it feels like that's the most natural way to detect that we had that we have a sibling, huh? But let's still carry on with this thought. And so, but the truth of the matter here is that how we relink the list, isn't that the result of implementing properly the CT merge algorithm? I think it is. So we're not going to implement this here. We are going to implement it. I mean, it's either both are done on append or both are done on read. But I think we need to do this on append because we can't, I mean, the result of how we relink is exactly the result of the merge algorithm. So let's try and figure this out. We're trying to implement D to append D, and it has the same CT parent. It has a conflict in the CT parent. But because we know, and so that's a subtree. Alpha 4, beta 5, beta 6. But since we know what, that beta 5 is greater than alpha 5, then we prioritize alpha 5 subtree in the linked list. And then we implement beta. Which should give us control del out, by the way, not control alt del. I think. But that's fine. What matters is that it ends up being the same thing. So we're about to insert the op. We look up the ref. And we need the ref. Don't we need the invert of ref then? Ref. The map to timestamp to maybe timestamp. So this will tell me that for beta 5, the ref is alpha 4. But we're not keeping track of other CT parents in that direction. We're missing the reverse data structure that will tell us, hey, you're trying to insert something that's already there. And for that, it needs to be keyed by the parent, not be keyed by the in that direction. So, but do we use ref in any significant way, really? Do we even look up? We inserted things in ref, but we're not looking up anything in it. So maybe it needs to be in the other direction. So it needs to give us the parent. No, it's not that it needs to give us the parent, that it needs to be indexed. I'm trying to figure out whether this would still be a maybe timestamp there. I think we need to revert it. Yep. So the key is maybe timestamp, which is interesting. And so maybe conceptually that's more like ref -1. We turn it around to have parents as keys to detect CT siblings. So it's more of a maybe ref -1 maybe. But let's keep calling it ref for now, and then simply insert oref in T in that way, and then oref, hold on, we need to see whether oref is a member, and then if it's true, then that we have a CT. Preemptive CT sibling. So let's try this. This should throw, but only after the first 4 tests. It shouldn't fail with the first 4 tests. But we have a, yeah, of course, we need to do some changes based on, oh, so it's only affected the tests. I think because in the test we have something where we actually introspect the structure. In here, yeah. And so that's sort of reversed now. right? This is yeah. So now we have nothing which points to this, and we have just alpha 1 which points to this. And then we need to do the same thing. Do we? Or are we done? Oh yeah, we're done. And then we have a preemptive city sibling, and but it doesn't tell us where. So let's add some info there. It would be in well, maybe let's get the log and the up. How about that? Show the log and the up. Show log and show up. What does it say? Beta 6, and what is the up? Up is beta 7, alpha 2 with code point 8. So that's a backspace. You know what? I actually want to project that log, but I don't think. Oh, yeah. If I do that, then there's a circular import. Is it a warning or an error? That looks like an error, right? Yeah. So do we move the types elsewhere to allow us to do this? I mean, we'll probably do this eventually, so let's do so. Types.birth. Module data.chronofold.types. Okay, let's say that these aren't types. Yeah, I think that sounds right. And for now, let's just copy all imports and then have the IDE fix that for us. And then from core, we import chronofold.types. Seems fairly happy with all that. And so now can we use project, and that's it? Seems like it. Yeah, okay. No, still a cycle. Because we want buffer to depend on types this time and not on Chronofold. And that fixes this, does it? Still so dot buffer. Yeah. And what you do here? No, you're happy. Good. here we'll need to export the types as well, right? And here we need to, well, what do we need? Oh, we good here. Right, so the preventive sibling here is at Pinsk. Because we did have a preventive sibling when we were adding up beta 7. Then there was something else in alpha 2. Absolutely, yes, there was. Very good. So we're catching something that we actually weren't catching necessarily properly until now. And that sounds great. And so what's maybe a problem here? That we're catching the primitive sibling here, but I'm thinking it's going to impact the relinking. And so that's, I think, what I need to convince myself of first. Let's go take a look at our example. Here. So we get to that crossroad where, in fact, I could comment out all of our previous tests for now, so that I have feedback with the proper example. There we go. Preemptive sibling CTRL, where we're adding beta 5. Exactly. And well, I'll look at this later. Yeah, exactly. Beta 5. That's exactly where I was expecting to have the problem. Very good. Okay. So first of all, let's maybe figure out why the test result until now were in the order that they were coming out. And they went past the buffer, so I'm going to need to I'm just going to return ref here. And so in our main, in our test, we first print one long control at del, and that is this. So this projects as cmd altd trl. Oh, yeah, I've only added beta here so far. So that's really what we're looking at now is more this. And then therefore, I kind of want to print that as well. That would be project of just append ops of this, I think. Will that work? Might need to $1 here. Yeah. CMD DTRL. Okay. Yeah, I think that's good enough to think about this. So CMD, and visibly it appends D first. In fact, maybe DEL. Yeah. So it starts by implementing beta instead of alpha, or implementing by let's say the weave goes in the direction of 0 CMD DEL and then backspace TRL, and that's how we get this with these two things struck. And so the linked list is really in position CMD, and here, okay, so NXT let's call it NXT prime. That's not where we want, that's where we have so far. And after D, instead of 5 alpha, it actually goes to A alpha. Then B alpha, C alpha, and then from L back to 5 alpha. That's what it does. But what we wanted to do is CMD. Indeed, 5 alpha. In fact, we wanted to do we wanted to do this. Because then we'll have CMD, and then we delete once and twice, and then we get to 8 alpha, TRL, and then DEL. Oh, yeah, A alpha, yeah, like this, like this. That's what we want. So without CT merge and with proper CT merge. Okay. So I see how, in fact, it is indeed tempting to do this in the at the projection level, because that's where we are. We are, in fact, relinking. I mean, we're following the we're following the link. No. It's better to do. Yeah, it's correct to do this in the relinking. Therefore, not in the in here. And so it kind of means that we don't. I mean, we are keeping this ref for tracking. So, but here, what do we do for real? When we find out that there is a preemptive CT, well, first of all, that's our case statement. That's fine. But what do we do with ref? We can't add it. So we really do need another way to detect this than using this ref array. So there's still something I haven't understood, obviously, about what's proposed here. It locates the new op city parent ref blah. Okay, right. So we get past the ref by the op, and we call it oref here. And from that ref, we were at least able to say whether we were inserting it at the end or not, whether it was ending with a thing. So we can probably extend that if we get past an array of timestamp here, which is our index inv. Then isn't that enough? Or could we make it so that it's enough and that we don't need that ref? So let's spell it out here. What does our index inv look like for our example? Well, first of all, let's just print it. Okay, so let's grab this guy. With alpha 12. Our code point array is this. Our next thingy is this. Our NDX map is like this. Our index inv is like this, and our ref is like this. Okay. So, and the op That's obviously after it's appended the thing. It's in that state where it's 10, 11, 12, which means in that next stage. So let's also carry this over. Right, it has the 10 here and the 11, 12, 5, exactly. So at the point where we receive 11, I kind of want to just print what we have. And that would be what that would be. 1 log CTRL, and then the op is going to be 2 ops del, and the first index of that. So let's also get this. Yeah, we have a nicely continuous thing. And our ops there we go, that's our ops. And this is really 1 log CTRL, and this is 2 ops del. And below is this thing. Okay. So we've got this upcoming. Which tells us its on time step is beta 5. And it's causally linked to alpha 4. Is there another way we can find out that something's pointing to alpha 4? This is next. This is ndx. This is ndx inv. And this is ref. Well, if we convert alpha 4, well, actually it tells us alpha 4, so we kind of know already. I mean, we can map alpha 4 to 3, right? And then we can look what's after 3 and see that there is something. And then we need to find out what is that thing, which is alpha 5. And then we recover our ref. Sorry. Why not? And so then what? Then we know that there's somebody here, and then we compare alpha 5 to beta 5, and we say, oh, actually alpha 5 needs to go first. And by that we actually mean all the city subtree. So once we know that the first leaf of our branch has priority, then we go ahead and go until the end. Do we? I don't even know what that would look like from the perspective of building the log, to be honest. I'm having a thought now. I'm wondering whether we're actually building the co-structures no, that doesn't make sense. I was wondering whether we're building the co-structure on read. We have op metadata that we need to do something with. And unless we're also storing the op metadata elsewhere, which is kind of what these co-structures are doing, then we wouldn't have anything to project on the other end when we read. So it doesn't really make sense. But I'm kind of starting to convince myself that this ref is actually maybe not needed. But I'm wondering about, like, we're following pointer references all around, and I'm wondering whether we're gonna have to do this now for all of the 3 beta operations that are coming in now, or whether we can avoid that, and then how. So, okay, I agree we can, by doing quite a bit of a dance, figure out that beta 5 doesn't have priority, and so in which case its insertion point would be all the way until the before to last structure. Yeah, so maybe we don't even need to calculate anything at this point. We're like, yeah, you don't have priority. We insert you at the end, and the end is kind of cur -1. I realize that cur is a terrible name for this thing. It really is end or last. Current local index. So if that's the case, then indeed we just add it at the end now. So it's, and which is a case that it seems like we already have. It's the case where we just do insert at the end. That's the one there, appending at the end. So let's call it end. And index or yeah, of the end of the local log. Sure. And then our cur, that means insert at the end. Except we're not going to be inserting this, I suppose. That's because we're inserting in next. But let me fix first curs, cur, and cur, and cur. Okay, and so we would be inserting, so we say, okay, well, it needs to be inserted at the end, and then we insert it at the end, and that's it. And the only other case is where we say, well, no, actually, it needs to be inserted. It has priority compared to whatever was there, and therefore we relink the list. And so it becomes very similar to this. And so it could be that, in fact, I mean, the idea would be that we make the cheapest calculation first to pick that branch. And can we do that? So if the ORF prime is where we have at the end, yeah, if we're just appending at the end, then that's a quick test, and we really only need to check if that's not the case, that we're inserting in the middle. Oh, hold on. What if there's several people trying to insert at the end? No, but the end by definition is there's nothing in there. So if we are inserting at the end, I'm trying to figure out whether this even makes sense. I think appending at the end this is hard for me to think through. Yeah, if we're appending at the end, by definition, there isn't anything else at the end. So that's the quicker test. And then it's only in the case that we're not appending at the end that there's a possibility that that there's a city sibling. Okay, very well. Therefore, we move this all the way down into this branch. And we don't know that we need to relink the linked list yet. We only know that there might be a city sibling. And so we need to do our thing. And it's not clear how we're going to check it yet. But maybe with this ref, and maybe in the future with something else. Maybe we could use the ref for now. And there might be a preemptive sibling, and then there's two cases. Then we have priority over the sibling, in which case we just do the same thing. We append at the end. Oh, well, so we append, oh, hold on. No, we don't append at the end. If we have priority, we append we relink the linked list, and if we don't have priority, like beta, then we append that, but not at the end. I think at the end of the CT branch. That's the thing. Yeah. Okay. So we don't. The sibling has higher priority than us, so we append. So we insert after the CT branch of the preemptive sibling. And will it look like? No, it won't be like that. It might be something different. It will still imply some relinking, but in a different spot. Yeah, that makes sense, and that's great. And except that we are going to need some branching here, but we don't know exactly yet how we're going to branch. And here we first test if we're at the end. If not, we need to check for preemptive siblings. So for now, that's being at the end. And then that's a way to check whether there's a preemptive sibling. Oh, yeah. And so the way that we could use our ref here, we need to use new ref. That's one thing. Or would we? Interesting. What I was thinking is we could make it so that we insert if there's if we detect collision in the ref array. I mean, we're going to probably change this, maybe trying to implement this with without this map. But while we have a map, we could make it so that if we want to insert something and then we're like, oh, hey, there's already a city parent there, then we could do the ordering comparison and insert the one with, let's say, maybe the highest priority. I think that would be what would make sense. That would be the max. And so some guy could come in later and replace that. And that would be fine. And that means we'd have a handle towards the beginning of the priority branch. And so then we can always use that. I was wondering whether, yeah, no, that will work with because of the relinking, I think. Yeah, the case I was running through my head was the case, but what if something of higher priority comes later? But that would be fine because we're relinking the list. And then we can update this guy, and then maybe future appends could then look it up. Okay, so let's try this. If it's true, we'll remove this map probably, but until then, we store the highest priority city branch. And so how do we do that? We know there's a member, but we kind of want to know which one, really. We don't really just need to do member here. We want to look it up. So we do lookup, not member. Yeah, that's right. And we get the priority ref, whatever. And here there's nothing in it, so then we just insert, that's fine. And then here we check whether the priority ref, we compare the priority ref to the oref, which is really the op ref. I think it would be better if I called it op ref. So let's do that. Oref, op ref. opref prime sounds good too. Ref, and we get. And so we compare with our prefs. And I guess we can bool that, but let's case it. I think that's in fact seems more readable. Such that if it's true, or actually compare, that does not give us an ordering. Oh, I don't even have compare yet. Here, yeah, it does give us an ordering. So it's what, LT, GT, and EQ, right? And that's pretty cool because we do have a weird case here where we're trying to insert the same exact thing twice, and that shouldn't really happen. We're trying to insert the same up twice. And so maybe we don't want to throw on this in the future, because let's say if the transport doesn't have unicity guarantees, right? If there can be, if we have duplicates, then we should be able to deal with it. We can just ignore it. So it depends on the type of guarantees we want from our transport layer here. Okay. So littler than, so our priority ref is littler than the ref that we're trying to add. So it means that then we do need to insert the opref. Well, in that case, so we're saying the opref. Okay, I think we should need to do it reverse. We have lower priority than the priority ref. In this case, we leave things be. We have higher priority than the priority ref, then we bump it. And so what's that? So modify it. That's not ordered collections. Pursuit and data map. Update, right? Oh, we could do that more elegantly with an update function here. Insert or replace a key value pair in a map. Okay, so I can just insert it. It's going to be happy. Good. So we just we insert the opref as well here. Okay, so now our ref has this feature of having this max value, and so does this mean we have a preemptive CT sibling member of ref? Member of ref. It should mean that, yes. And so at this point we look it up, then we kind of need to look it up. seems like we're going to need to duplicate that code. Which, it's so interesting. I wonder whether that basically tells us that's a kind of a code smell for the fact that we don't need this. But it seems like we will need to duplicate it for now. So we look it up. And then there's something in there. And in this case, if the opref is if we are of lower priority, so that's the is there a city sibling? And that's there isn't. There isn't a city sibling. If there isn't a city sibling, then we can do our insert or our relink. I think in the normal way, which is this. What's next prime supposed to be? Oh, here. Okay, that thing. Okay, and then we need to do this case, which is this case, right? We are lower priority than priority ref, so the sibling has higher priority than us. So we insert after the city branch of the preemptive sibling here. And I don't know how to do that yet. That's a little bit involved. But then if it's greater than, then we back and we do this thing again. Same thing. So can I make that where a let and put it here? Such that if we have higher priority, then we do the insert and we relink. And we also detect about inserting the same op twice here, which I guess is fine for now. And then our tricky case is here now. So it's going to be a bit like next prime, right? But next prime, but it's going to be next prime. Why not? And what will this do? So we need to insert after the city branch of the primitive sibling. I'm not even sure whether that's a proper place for let here, to be honest. I think it maybe needs to be before the case. So what we did here is that we looked up, we did our back and forth conversions. And I'm going to need this this stuff here in view. Yeah, I mean, I already know it. I don't need the editor to tell me. That should be correct. So I suppose we could put all this here for now. Okay. So we've received this beta 5. We've looked it up. I'm missing a branch here, I think. Test if we're at the end. True. We just append. False. There might be a primitive sibling. We check it. In the just case, a few possibilities. And nothing case, a few more. So this doesn't exist anymore. Okay. So we receive beta 5. We look it up. And in our ref, oh no, we receive ref alpha 4, right? And then we look up alpha 4. And we're like, ooh, hold on, alpha 4 there's something in there, and it's alpha 5. Okay. So priority ref is alpha 5. And we compare the two, and this is beta 5, this is alpha 5, and we're like, nah, the sibling has higher priority than us. So then we insert after the city branch of the preemptive sibling, whatever that means, and that's where we are. And so that means what? It means that we need to, so we kind of need the priority ref. That would be useful to have. And so maybe we pass it to our next prime, so that we can do something with it. And we'll call it pref here. So now we have alpha 5. And so we need to follow, we can't just append at the end here, right? We need to follow this all the way until where? Is it really until infinity, the terminator of the linked list? Which would be the kind of the spine, you could say, right? It's like the thing that stays straight in some way. Meaning in this diagram, would say, you know, whatever is we consider being the priority is the thing that sits at the top. If there's something that comes in, then poof, we change it and we put it at the top. And then if it's at the top, then it kind of runs until the end, really. And then everything else that's between is sort of conceptually spliced in. But so here we say, well, we insert backspace. There's already a parent. Okay, I lost myself again. Yeah, I'll take a tiny break. And I'll be back. And I'm back. All right. So is it the case that when I see that I need to yield to the existing no, that there's a case, I think. Isn't there a case where you have something a bit like so we have a 0 and let's say we have A, B, C, and then we have some D, E. Right, and then, well, yeah, that's it. That's the case, right? So in that case, we're like, oh, we're coming in as F. And we're like, well, actually, D already has, so we have a sibling here, but it has priority. So therefore, we need to insert F after DE, but certainly not up until the end, until infinity here. So indeed, we need to follow the branch. And so what that mean? And do we need to, we probably need to do a test with that. That's for sure. So let's add one conceptually. Let's even maybe name it. It checks replication with conflicts and let's say sub-CT trees, oh well, sub-causal trees. Okay. Well, we can actually say that this fails. So in that case, how, yeah, what does it mean to go up until the end of a branch of a tree? So if it was the reverse, in fact, right? If let's say we were adding alpha 6, 7, blah, and this was beta, blah, then we would need to, or let's, can I even scenario this? I'm not sure. I think I need to do it in my head. Yeah, this is not going to be easy. So let's imagine that we had, it seems like that's when actually having things, I mean, basically we need to follow the, is it the case that we need to follow the chain of the parent? While its replica ID stays the same? maybe. Because I think we are talking about local orderings and that the replica ID is essential to that. So really the concept of a branch really only exists because we have each branch belongs to a different replica. So do we have something that helps us in here, for instance? Does ndx-inv help us in the sense that we can just pick alpha 5 and, well, we need to find it, but we can do that with the ndx. And then when we have ndx, then we just continue reading ndx until we have something else than alpha. I wonder if that's true or not, because couldn't we have like a G here that would be coming from another replica? So let's say that this was, I'm inventing new notation all the time. That's not good, but alpha, let's say this is alpha 1, alpha 2, alpha 3, and then that would be some beta, but that would be maybe some delta or something. We have alpha 2, 3, and then we'll have alpha, this would be beta 1, but actually beta 2 would make sense there, right? Like something where we've only seen alpha 1, so we are at beta 2. And then this would be beta 3. And then we have a gamma comes to play, and that could be gamma 3. And so the question is, could we have like some kind of delta that would just show up? And that would be, I guess, something like a delta 4. And that in that case, it's something like maybe the beta replica, maybe there's a network partition, and the beta replica gets some up from a delta. And it depends it at the end because it makes sense in that sense. And it's low priority, that's all good. So in theory, then I think it makes sense that the list will be relinked in that way, right? Because alpha will have priority by virtue of being replica 1 and our global order, or ATO, I think, right? Our, what is it called? Our arbitrary, I forget what ATO meant. ATO, arbitrary total order, yeah. And so then when F shows up, it does have several choices, right? It can be relinked as ADF and then EG blah. Oh, there's no need to go until the end. There's only the need to relink to the next thing. Huh. I'm confusing myself. That's what's happening here. So there's no such thing as until as what I said here. How did I put it? we insert after the city branch of the preemptive sibling. It's not city branch here, it's what? It's now what the trouble is that this isn't a proper example, right? Okay, maybe this will help. So our beta 5, no, it is after the whole branch. How come? It is after the whole branch in this case. There's really no fiddling with that. We need to do the backspaces and the TRL before we write the DEL. There's no... Okay, I actually want this written in the style CMT, right? And DEL, that's convenient. Except okay, this is alpha 2, yeah. 2, 3, 4. And yeah, no, so this comes after D. We can leave out. And so if we do relinking, then we're really inserting here. Alpha 5 is this, yes. Alpha 6 and 7. And 9, right? Alpha 9, yeah. With beta 2, depending on alpha 4. It's not 2, it's 5. DEL 5, 6, 7, depending on alpha 4 and whatnot. And so really, indeed, what we're saying is that if alpha 5 has priority, then we do run this until, I suppose, the end of its branch. Well, you know what? Let's implement it as until the end of the world, and then implement this test and break it. That's probably a nice iterative way to do it. So we have a priority ref, and that's alpha 5. And so when we're looking at our NXT array, our next array, at this point it's looking like this. And so arguably, so if we say we follow it until the end, then we just say we don't really need the pref. Like, so fine, let's say we don't need the pref. I think we will need it, but let's imagine we don't. I mean, no, it's absurd. Like, I'm gonna end up saying adding it at the end, which turns out to be exactly the next prime case. No, the next prime is the relinking, so it turns out to be this case. We just insert it at the end. Okay, well, I guess it's easy to implement. So this should work for the naive case. Maybe it will even work for a command Control-Alt-Delete case. And if not, we'll just implement that other test. And so I think we can comment that out, and then now it should make its way towards compiling. Okay, this case should be, maybe this indentation there is causing trouble. Oh, so actually that let doesn't work. So I guess I'll revert back to a where. And we need to import these guys from ordering. And what's the deal now? Oh, yeah, right, that's end. Oh, right. The result of the lookup is a maybe. To be honest, this is the So now you're saying this is a maybe, even though we've pattern match on it. So that means that we're in ref. Are we really storing? We're not storing maybes of maybes in ref, are we? The keys are like that, but not the... Oh, maybe because upref is a maybe. Is that the issue? Maybe upref is a... Yeah, of course, upref is indeed a maybe value. So can I actually... no, I'm not going to be able to deal with this properly. Oh, I guess I could just compare it with just priority ref, can't I? So that's slightly weird. And but it compiles. Well, not really. Uh-huh. It does build. Okay. Control del seems right. Huh. So we did fix one of them, but not both, and I think that's right. Control del alt. Yeah, that's sort of what I was expecting. And so, but the other ones are not working, and so good. I mean, good job from Archagon to have picked up an example which actually does exercise the failure path of a merge algorithm, a naive one. Okay, so indeed good. Now let's try and implement this correctly. By having an x prime, and then we need to pass this pref. It's pretty clear, and it will be in this case, and we'll need to make it x prime of priority ref. And we'll need to do the proper relinking. So let's get our stuff below. And let's think again. So let's do what I was saying first, which is that we follow the linked list for the same replica. So maybe you won't deal with that case, which is probably a more complex, and I'm going to add this on tests. That is a more complex replication with subcausal trees, and I think it would have. It does have potential to actually happen in the real world with the partition, as I mentioned. And complex, and like let's say partitioned subcausal trees. Something like that. So really the index, I mean the data structure we could use is the ndx-env, right? So we get our pref, our priority ref. We check inside ndx. Oh no, we know it's alpha 5, right? So we know it's alpha 5, so we do need to check where it's at in the ndx-env map array. So for that we can use the map. So we look up pref in ndx. And that would be in ndx priority, so whatever, right? It's the branch, it's the index, it's the start of the branch that has priority. And then we kind of need to, well, we need to indeed the same way we get into the ndx-env array at this it's the ndx-env array, right? That's global at this point. Yes, it is, but it's without the cap. Okay. And then we look up at ndx priority, right? No, we don't. We need to scan it with some predicate. So that's data string, that's data array. So find index for which the first index for which a predicate holds, and the last index for which a predicate holds. That might be the right way, but we need to start with the subarray that starts at ndx priority, which I guess we could do that. But we need to tail it, right? I take and no, that's not that. Right, we could just drop indeed. So and drop ndx priority, and so that should give us the subarray we're interested in, and then we could take while, I suppose, as well. That gives us back an array. We don't, what do we want out of this? We want to know the last the last element such that, so it's kind of a while. Yeah, it's more of a while. And we need to get the last element. So it is the one we saw earlier, which was find last index. Yes. I mean, actually we want to find the last element, lm last index. The last index for which a predicate holds. Oh, you mean what? Okay, yeah, so there's no way to get the last element instead. Set by get range. Doesn't look like it, so we need to do this in 2 steps. That's fine. So we find last index within that guy. For the predicate, that's going to be what? Same replica of then pref. So pref is a timestamp, right? So that should have a replica right there. And so our predicate function really will be deconstructing the timestamp into some r prime and something we don't care about. And it will check that r equals r prime. Find last index, predicate, array, and it will give us some kind of int, which is the ndx last, ndx priority last. And then we'll need to find the element. Or do we even need the element? Because now this is where we need to do our splicing. So we're kind of in the next spot as we were with the relinking, right? Which is that is that the swap? Is that the thing that we need to swap? Oh, so with the next of the ndx index, right? Yes. So that's in this case that would be the thing that's sitting here. And so it is kind of where we swap. And so saying that we swap with infinity is actually, so maybe we do that. We swap with this. And so let's think for a second. And then what do? We would update. Okay, well, at where we'd update whatever is at that last thing. Are we talking about the next array? So we have a next array that's like this. NDX priority last should be this index. So 0, 1, 2, 3, 4, 5, 6, 7. And so we're saying we update at 7 and we put there the highest we Is there 9? We already have 9 there. I mean, there is a swap to do, but let's understand the insert first, maybe. Oh, so it's not at the end, right? Huh. So maybe... that is kind of where it starts. But we ignore where it starts. We care about where it ends. And in case where it ends is not infinity, then we still need to do this proper relinking. Which is that wherever that next was with the infinity, we put 10 there, and that sounds right. So the length of C is actually 10. And so we put 10 at the last priority. Yeah. And then we insert so here we only are adding, let's say, beta 5. So then infinity becomes 10, and that's it. So we just insert at the end the next swap. I think this might work. Let's try it. Find that index. And drop. We might need to put $1 here. And okay, we need some parentheses. And there's some shadowing there. Okay. So say R1. No, that's not going to be shadowed, and we don't need this. Okay. Okay, we have a interesting error. Error relinking the linked list. which could be any number of places. Including the one we're surveying now. So let's add some info up there. See whether we're hitting the right one. Log priority ref. I mean show priority ref. It should be alpha 5. Alpha 5. So we are hitting the right thing, which means that our next prime is yielding nothing. So let's check it again. We might need to spy things here, but then so we are looking up alpha 5 inside NDXM. And in NDXM, alpha 5 should give us 4. So NDX priority is 4. Then we drop, oh, yeah, if we drop NDX priority, then I'm going to need to add NDX priority here if I want to have an index that's correct. So let's start with that. And we still have a problem. It's all good. And I think we want to spy on this. But also spy on that. And I think the error is preventing us to, or unless it's short-circuiting. Oh, the last index for which a predicate holds. So maybe, no, I think that looks right. Oh, what? Yeah, no, it doesn't look right at all because now it should be this. Oh, hey, you are okay. Okay, so stuff happens, but clearly we've been mangling now our array, which is fine. Let's check our execution. So I think I want, and so NDX and NDX priority last is 8, but I think I want each separate. So let's do that. To be a little bit ugly, but it's fine. This and this, is that gonna just work? Looks like yes. Four and 4. Four is right. If we drop enter here, then 0, 1, 2, 3, and then 4 is the infinity thing. So maybe we need to do this before the infinity and do -1 then. Well, be right back. And I'm back. So we're sort of, so here the value we get is 8, which sounds like probably we don't need to do the -1. Oh, that's if we care about the value, which we might not. We might care about where we are in the index. That's the... So we might not care about the actual value. Oh, right. The NDX web thing, that's just the... I remember now what this is. This should contain infinity, in truth. That's what we want. So is that what we get? Yeah. Okay, so that's fine. And then we do what? Then we put... I think we put NDX priority here. Whoopsie. Saying that in fact... Oh no, hold on. This is not about priority. Isn't it about our up? That's what we had. That's what we want. That would be ndx. Oh, that would be upref prime, right? But instead of swapping it at the causal parent position, which is ndx index, we swap it at this position. So let's check on next prime here and what it looks like. Seems like maybe that will help us understand what's going on. Next prime. One, two, three, four. Oh, right, so definitely not priority, definitely priority last. And then next swap should have infinity, and we add that at the end. And that sounds right to me. So let's try again. Okay, right, I need to check a particular one. Which one do I want to check? The first one? Oh, well, wait, there's two infinities there, so clearly we're messing things up. Yeah, I definitely don't need to do this elaborate thing here. I can just say, show me next swap here. And maybe I want to, nah, I don't know if I want to do that. I need to know where I am in the loop though. So, and did we crash? We didn't crash this time, right? Yeah, no, we didn't. And we're supposed to be in this branch, right? But since we don't crash, we don't see this, and therefore let's spy on things. Spy on log and up somewhere. Maybe just ignore those. So if we say something like const spy, let's get the up. That should work, right? Or except it's going to do the next thing first, but no, it should be fine. I should still be able to read this. It's partial, is that what you're unhappy with? No, you're just not doing consting correctly, or consting. Need to do const A then, I think. Yeah. And okay. Right, so the op is afterwards. And so here we have beta 5. I could actually spy on show op, that would be better looking. Timestamp beta 5 pointing to alpha 4. So it seems like this is the correct case. And so at this point, next prime is already not in an order that sounds, but maybe no, this order seems like it's not the right order. Let's thin out our tests, make sure we're not testing too many things at the same time. I mean, there's lots of I mean, we shouldn't go in this branch too often, but I guess if I comment this out and I also comment this out and this, then I think I should be building pretty much just the right things. Yeah. So next prime is already ordered the wrong way for some reason. And I'm spying this one. Oh, because it's already been swapped. Yeah, of course. So let's just spy next. That should give us the fuller picture. Okay, next is nice and ordered, which is what we want. But now, for some reason, we're swapping here. Which clearly means that we do need to... yeah, we need to update at ndx priority plus ndx priority last, because that's what we've been doing here. So maybe I should just say that this is plus ndx priority and stop with that nonsense. And just say last here, and last here. And probably we can do, oh, right. We need to do plus blah ndx. I might need to make it inside a just here. And Do I need to section this? I think I need to adjust this. Okay, that looks more ordered now. 9, yes, and so that's next prime before I insert at blah. So the final result, well, actually the test passes, but well, yeah, but I don't really have a test anymore. Okay, but let's check. Let's check what the projection looks like now. And we're really interested in this guy. That's the main guy, I think. Right? And that's Control Del, which is how it should be. So let's roll drums. And yeah, we don't have those guys anymore. That's all good. Control Alt Del. And Command Del. Okay. Okay. So not yet, but on the way. I mean, I think this Control Alt Del we already have. It's this guy, right? Yeah. Okay, so let's make sure we only troubleshooting what interests us, which is these 2 log Control Alt Del right now. And that means we can probably avoid this and this. And be okay. Yes, indeed. Okay, so let's check what happens with ordering here. And I think I need a view on my resulting next, in fact. So just spy on A here. Although it would be nice to have the up as well. So oopsie, let's keep the up and also spy on A. A being next prime. Okay. So this is for when our up is alpha 5, depending on alpha 4. The backspace. So that's fairly that I think is the first step in here. Ah, right. Except this, in this case, we shouldn't go inside the priority sibling case. We should go into this guy, the lower than, right? Because there should already be a city sibling. Yet, it seems that we do enter the branch. I mean, there should already be a city sibling. I mean, there is. I mean, it sounds like, though, that this adding alpha 5 it feels like that's the normal case. Why? Right. Because in the 2 case, we already appended the CMDDEL. So we already have a beta 5 that's refed on alpha 4. And we receive the ops from 1, which is a backspace 8, which already is. And so there's a test that's not working properly. This should not go into the LT branch, it should go into the GT branch. Indeed, we have higher priority. So why don't we go into the GT branch here? So we look up opref. Should this be opref prime? No, it doesn't need to be because our map actually contains is indexed with this maybe thing. So this is not this case anymore. This case actually works. Seems like. How about I compare upref prime with ref? I'll just spy on this, huh? So you're going to tell me LT, which is strange. LT. So I need to know what you're comparing here. Alpha 4. Oh. Right, I've got my orderings backward. Huh. I do, and I don't think, let's see. Well, let's have them in the other direction. I was expecting alpha to have priority. I mean, it's arbitrary, but... Okay, so now it's GT, which is fine. And then sometimes it's LT, which is also okay. And then it... Ooh. It outputs control at del. Did we get it? Let's first check just on the alpha replica. Control at del. Control del out. Okay. So it's like a Rubik's Cube a little bit, no? Okay, well, very well. We know what to look at. So we start with a, so we never go into the, LT branch. Whereas, oh, right. Yeah, because the 2 ops are going to have priority over the 3 ops, and then the 1 ops are going to have priority over the 2 ops. So indeed. So then it means that I did do that on purpose here, but to append these ops and only then these ops. But maybe I didn't do this properly because well, let's check whether if I do this in this other order, whether it will work or not. Control del alt. Okay, well, at least it's commutative, but it's not giving us what we want. So So maybe that's a nice place to stop. Hey Juan, what's up? Those are funny. There must be a problem with my notifications. I'm not sure why I haven't heard you. Oh, because my chatty is started but not connected. That's why. Hey, good to see you. Well, you arrived just at the end. I got 2 out of my 3 tests passing, which is pretty cool. And so there's still a little bit of a investigation to continue with. Yeah, we're almost there, and I think a couple of streams to figure out this merge algorithm is pretty reasonable, given that that's the kind of complex bit. So let's. I'm kind of famished right now, so I'm gonna get myself some food, and then yeah, come back tomorrow. And let's see, tomorrow is tomorrow is the last day of 2020. That's one thing. It's also Thursday, so it's all good. It's just regular weekday things, and yeah, what can we say in our log before signing off? That well, this is in progress, implementing the CT merge algorithm. So yeah, I guess we don't really have a proper update to the log quite, but I'm still gonna commit and sign off on after that. So let's commit CT merge algorithm partially implemented. And I might need to no verify this so that it doesn't run my commits, and then push it. All right, and that's it for me for today, and thanks for watching, and I will see you tomorrow. Bye bye.